Well, welcome everybody. Today is going to be a really exciting class, so make sure that you pay close attention and you don't look at anything else unless it's like something that I tell you to do. So first of all, here's what we start with. You must have, can you see that clearly, or should I switch to a darker color? Let me switch to a darker color. You must have two primes. I'm going to call them P and Q. And based on that, we're going to define the variable n. Let n be p times q. So does that seem very hard? You just have to have two prime numbers. You have to let a third number equal the first two numbers multiplied together. And then you have to you choose this number. So this number n is defined. You can't choose it. It's just always p times q. But then this third number you can choose though. Choose e that's relatively prime. Relatively prime. So relatively prime doesn't mean like partly prime. That just means it has no common factors with something else. Choose E to be relatively prime to the product of P minus 1 times Q minus 1, like that, which is not going to be prime because at least one of P minus 1 or Q minus 1 would have to be an even number. So when you multiply by an even number, you get an even number, which is probably not prime. So choose E relatively prime to P minus 1, Q minus 1. That just means it has no common factors with that. Then calculate. So far, the only thing you've really actually done is just three things. You've chosen P to be a prime, you've chosen Q to be a prime, and you've chosen E to be relatively prime to the result of P minus 1, Q minus 1. Then you have to do one more thing. Then you calculate D, which is called an inverse. And we've already done this before. So there's a unique inverse of the number E mod P. Sorry, hold on. My writing got mixed up. Mod P minus 1 times Q minus 1. So and then what does this actually do? So what you've actually done right now is you've actually set up how encryption works. You've actually set up how encryption works on the internet. So like if you have go to a website and you have a secure certificate and you encrypt your data as you're going to your bank's website or any other website that's encrypted, this is how it works. So the equation for encryption is like this. Cipher equals message to the power of E mod n. And then the original message, to decrypt it, the message is equal to cipher to the power of D mod n. So it's actually almost laughably basic how it works. All you do is you just take your message to the power of E mod n to encrypt it. And then to decrypt it, you just take your encrypted message to the power of D mod n, which is actually mathematically, this is not even encryption at all because all you have to do is just factor out the value of n, and then you can decrypt it because you can figure out what P minus 1 and Q minus 1 are, and then you can calculate the value of D and so forth. So why is this encryption? Since mathematically there's nothing at all that's encrypted about this, really mathematically. So why do they call this encryption? Because here's why. You tell everyone, this is called public information, the value of n and the value of E. But you don't tell them what P is or Q is, or what P minus 1 or Q minus 1, sorry, or what P minus 1 times Q minus 1 is. So nobody else knows what the two prime numbers were, or what 1 minus the two prime numbers was, or what the product of the two of 1 less than the two prime numbers is. So just because they don't know that, that means in order to figure this out, there's still mathematically there's still nothing being encrypted really, because if you know the number n, you can just factor it apart to find the values of p and q. Because if there's only two prime numbers that go into another number, that means that the only factors it will have are those two numbers. So it just has to be factored out. So why is that such a complicated way of encrypting something? Because how do you find the prime factors of a number? Does anybody know how you find the prime factors of a number? Well, first of all, you check to see if like it's divisible by 2, for example. If it is, and you know it's even, then it's not a prime number. And then you check to see if it's divisible by 3, and then you check to see if it's divisible by 5. So you have to check to see if a number is divisible by every single prime number in order to see what its factors are, right? And if you choose a really big prime number, like maybe 300 digits long, then it's going to take billions and billions and trillions of steps to check all the other prime numbers. It's not really actually as strong as it sounds like, though. Why not? Because in order to find the factors of a number, you only have to try numbers up to the square root of a number. So if the number has 300 digits in it, the square root of it will only have about 150 digits in it. So it's actually less difficult than it seems, but even 150 digits is still an awful lot of digits, though. But as far as everybody knows, there isn't a way to find the factors of a number without checking to see if it's divisible by various different prime numbers. Although, if you think hard, there probably is a faster way, because you probably have a computer program that picks the prime numbers, and if you looked at the code of the computer program that generated those two prime numbers, there's probably some similarities between how it picks all of its different numbers. Like maybe it always picks them within a certain range just by chance or something. So there might be a way of narrowing down the results and then factoring it out. So basically, encryption like this is based on the fact that you assume that you can't factor out a number very well if it's big enough. Okay, now let's try an example of this. So let me erase the bottom part, and that's just irrelevant to the mathematics about what you tell everybody about. So let's erase that. So I just want you to know that it really is possible to decrypt things. There really is nothing actually truly being hidden by this encryption. It's just that it would take many years. Supposedly, it would take many years to find the factors of n. I mean, but if you know the factors of n ahead of time, then it's easy to find the answer. Okay, so let's go ahead and do an example. Okay, so I'm going to pick the prime numbers for us. Okay, let's do a new page. So I'm going to pick the first prime number to be 7. So make sure you're watching. Are you watching? Are you watching, Isaac? Isaac, you're not even listening or watching. Isaac, take off your headphones. Take off your headphones. You're not listening. All right, so we're going to choose P to be 7, and then Q to be 11. And then what's P times Q? Correct. And now we're going to calculate what P minus 1 times Q minus 1 is. So what is P minus 1 times Q minus 1? 60. Yep. So because P minus 1 would be 6, Q minus 1 would be 10, and that would be 60. And then now we can pick any for E. What's the requirements of E? Let's go back and check. E has to be relatively prime to P minus 1, Q minus 1. That's a very important restriction. You cannot just choose anything for E. So let's go back and look at what P minus 1, Q minus 1 is. We need to have a prime number that has no common factors with 60. So we can't choose 5, for example. So to make this easy, I want to choose the smallest one. So 1, 2, and you can't choose 1 because 1's not a prime number. So 2 is not work. It would not work because 2 has a common factor with 60. And 4 obviously would not work. 5 would not work. 6 would not work because 6 goes into 60. 7 would work though. 7 has no common factors. So I'm going to choose 7 because that's the smallest one that would work. And believe me, the bigger we choose it, even a slightly bit bigger, it makes it harder. And then the message I want to encrypt is going to be the number 2. So the message I want to encrypt is the number 2. And then who remembers how to encrypt a message? By the way, in order to encrypt things, your message that you're sending, like the text that you're sending, every single letter of text represents a number. It's called the ASCII table, or the UTF, the Unicode Transformation Format number 8, UTF-8. They have various codes and things, and they, in fact, sometimes they even take several letters together and put them all together into one block, like a big number. But they break up your message into groups of numbers. So I know you don't think of yourself as sending a number through the internet, but you basically, whatever text or file you're trying to send, it's broken apart into numbers. And then each of those numbers is treated like a message, and then you need to encrypt it. So what's the formula for encrypting a message? Do you remember?
Message to the power of the N.
Yep, exactly. So the cipher, or the encrypted part, is equal to the message to the power of the encryption power, mod n. So let's encrypt this message. Ready? So the cipher for this message is going to be 2 to the power of 7 mod 77. So what's 2 to the power of 7? So just take, you can do that on a calculator. 2 to the power of 7, 128. So this is equal to 128, but then make sure that you do mod 77 at the end. So what's the remainder of 128 after you divide by 77? So basically just subtract 77 from 128, and what's left?
51.
51, perfect. So the answer is the cipher. The cipher, or the encrypted message, is the number 51, like area 51. So encrypted message is like area 51. Now, how do we decrypt it? So what we do is, remember back in our requirements that after you choose E, which you can choose E to be anything, you can choose E to be any encryption key. E stands for encryption. Any encryption thing that you want, as long as it's relatively prime to P minus 1, Q minus 1. But once you've chosen E, though, there's only one unique decryption key that will work, though. It has to be the inverse of E, mod P minus 1, Q minus 1. So we already talked about how to find the inverses of things, mod certain numbers. So the inverse of something mod a number means that, so the inverse of E, let me put the box right here. The inverse of E mod 60. So 60 is the value of n minus 1. 60 is the value of P minus 1, Q minus 1. What does it mean to say find the inverse of E mod 60? So the decryption key will equal the inverse of E mod 60. But how do you define the inverse of E mod 60 though? So that means if you take the encryption key E and you multiply it by the inverse of E, you'll get 1 mod 60, right? Just like the inverse of 7 is 1/7, because 7 times 1/7 equals 1. And so when you take the encryption key times the decryption key, that'll be congruent to a 1. Now, it can't really equal 1, actually 1, because you're not allowed to use fractions. These are always integers. So when you multiply an integer by an integer, you just get a bigger number. But mod 60, though, you can get 1. So encryption key times decryption key has to be congruent to 1 or equal to 1 mod 60. So that's the hard part. But it's not very hard, though. All you have to do is just keep multiplying things of 60 together until you get to the right one. So does it have to be bigger than 60 or smaller than 60 in order to have a remainder of 1 when you divide by 60? bigger, right? So like, for example, 61 would have a remainder of 1 divided by 60. So let's go ahead and think about this. You have to think about this kind of like mentally. It's like a little bit hard to do at first. So we want to multiply 7 times a number that would maybe equal something like 61. So does 7 actually go into 61? No. So there's another number that would also have a remainder of 1 when you divide by 60. So what's 60 times 2 plus 1? 121. 121, when you divide by 60, it would have a remainder of 1, because 60 goes into 120, and then you'd have 1 more, right? So the question is, since E is 7, can you multiply 7 by a number that would make it equal 121? So does 7 go into 121 or not? No. So rather than keep on trying it slowly like in our heads, let's just go ahead and calculate what. So we already tried 60 plus 1, which is 61 divided by 7, and that did not work, right? 60 plus 1 does not divide by 7. What about 60 times 2 plus 1 divided by 7? That'd be 121. That does not work. How about 60 times 3 plus 1 divided by 7? That does not work. What about 60 times 4 plus 1 divided by 7? That does not work. 60 plus times 5, okay, that works. 60 times 5 plus 1 is divisible by 7. So what exactly is 60 times 5?
300.
300. And what is 60 times 5 plus 1? 301. And so that means then the answer is 7 times 43 equals 301. And 301 is congruent to 1 mod 60. So the answer is going to be 43. So what we just figured out was this. We figured out, oops. I don't know what happened. Okay, so I just swiped and then everything got goofed up for some reason. Oh, that's the problem with touchscreens is whatever you touch, if you just happen to touch the wrong thing at the wrong moment, it can do something weird. Okay, so what we figured out was 7 times 43 is equal to 301, right? Which is congruent to 1 mod 60, right? So therefore 43 is the inverse of 7 mod 60, right? Okay, 7 times 43 is equal to 1 mod 60. So that means the decryption key is 43. Let me just double check, make sure that's right. Okay, perfect. Yep. That's what I got last time. So the decryption key is 43, and it's very easy. Theoretically, it's very easy to do it. All you have to do to decrypt the cipher and change the cipher back into the original thing is, so let me write this up at the top in a little box. The decryption key is equal to 43. All you have to do to decrypt the message is what? Did anybody write the formula down?
Side to the power of D on N.
Yeah, right. So the original message is equal to cipher to the power of the decryption key mod N. So we're just going to take 51, which is the encrypted message, to the power of 43 mod 77. Because remember, N was P times Q, which is 77. Now this is where even with a very small start, like we picked the numbers 7 and 11, even at the very small start, like just 7 and 11, you still have a huge number to calculate. 51 to the 43 mod 77. So the strategy to do this is actually to break this up into, so we have already learned about the binary exponentiation theorem for modulos, right? That's a little hard to understand though, so maybe I won't use that method on this problem. But all you need to do is break this apart into several factors and then reduce each of those factors. So let's just take 51, put it on the internet, and figure out what the remainder is. So actually, what is 51 mod 77? That's a trick question, but what is 51 mod 77 by itself? What?
Is it 0?
No. It's actually 51 because 77 goes 0 times into 51. So it is 51. So you can't reduce it as is. But this is why the binary expansion theorem works. What is 51 squared though? 51 squared would be bigger than 77, right? So the remainder of it would be something smaller than itself. So let's write this message like this. As 51 squared. Do you see that? Now, how many times does 2 go into 43? 20, you're actually right, 21 times, yeah. And what is 2 times 21? 42, right? So there's technically one extra 51 left over, right? So 51 to the power of 43 is equal to 51 squared to the 21st power times 51, right? And then mod 77. So let's go to the internet and let's open up. So here's a web page. Let's push sorry, I pushed the wrong button. Oh, there we go. Okay, it's F12 to open up the coding console. So let's just type 51. By the way, to do a square, you do on this thing, you do a double star. 51 squared is 2601. And what's the remainder of 2601? Mod is percent, remember? What's 51 squared mod 77? It's equal to 60. So that's kind of cool. 51 squared mod 77 is equal to 60. So remember when you're calculating a modulo, you can replace any term in the any factor, I mean, like 51 squared, for example, you can replace it with what its remainder is. So 51 squared has a remainder of 60 when you divide by 77. So this actually equals 60 to the power of 21 times 51 mod 77. Then we're just going to repeat that process. So how many times does 2 go into 21?
10.
Yeah, let me write this on paper though, by the way. Then copy it to a new screen. So hold on just a second. So I have 60 to the 21 times 51 mod 77. Okay, perfect. Now I'm going to start a new screen. Sixty to the 21 times 51 mod 77. So like you said, I can reduce this to 60 squared, but you said 2 goes into 21 10 times. So if I put it to a power of 10, 60 squared to the power of 10 is really 20, right? So 2 times 10 is 20. But I need 21 though, so what do I do since I don't have a power of 21 anymore? That just means I take the last 60, the last power of 60, and I just put it to the side, like that. So what I have right now, it still represents 60 to the power of 21. And then I still have the extra 51 to the side. So now I'm going to go to the internet again and calculate what 60 squared is mod 77. So let's do 60 to the power of 2 mod 77, and I get 58. So let's put in 58 for that. So 60 squared has a remainder of 58. So then I have 58 to the power of 10 times 60 times 51 mod 77, like that. Now how many times does 2 go into 10? So I could reduce the 58 to be 58 squared to the power of 5, because 2 times 5 equals 10, right? And then I still have this. Actually, let me reduce the 60 and 51. There's no reason to keep those separately. I'm just going to do 60 times 51 on the computer. So 60 times 51 is 60 mod 77. That's 57. So 60 times 51 times 51. I forgot what it was. Sorry. It's 57. So both of those two together have when you multiply them together and you do mod 77, you get 57. So now I have 58 squared to the power of 5 times 57 mod 77. Now I'm going to calculate what 58 squared is. So what is 58 squared? Oops, no, by the way, I used the wrong key just by habit, because when you use the normal power key on the computer, 58 caret 2, that does not mean, that means XO, that actually means XOR, I believe. No, that means, yeah, I think that actually does mean XOR in this particular language. So you can't say 58 squared like that. How do you say 58 squared? Double star. So 58 squared is 58 double star 2, and then mod 77 would be percent 77. Then you get 53. So 58 squared has a remainder of 53 when you divide by 77. This is going to be 53 to the power of 5 times 57 mod 77. There we go. Wow, this is interesting. So how many times does 2 go into 5? 2 times. So I could reduce this to 53 squared, right? Times 2. 53 squared to a power of 2 is a power of 4. But there's really supposed to be a power of 5, right? So that means my last value of 53 to the power of 5, my last 53 needs to be written beside 53 squared. So my last 53 goes to the side next to the 57. Mod 77. So let's calculate what 53 squared is mod 77. So 53, sorry, hold on. 53 squared mod 77 is equal to 37. So that's 37. So that's 37. And then let me calculate what 53 times 57 is. What is 53 times 57 mod 77? That's 18. 53 times 57 mod 77 is 18. So 53 times 57 mod 77 is 18. Now, by the way, once you get far enough, you can stop and you can just type in the whole problem into the computer. The reason that you can't do the original problem in the computer is because 60 to the power of 21 is more digits than the computer can even calculate. So you have to logically break it down most of the way. But once you get to this point, though, 37 squared times 18 is something the computer can easily handle. So once you get it to that far, you can just type it the whole thing into the computer. So let's do 37 squared times 18. So 37 squared times 18 mod 77 is equal to 2. Okay, perfect. I forgot what I was even doing. Okay, is equal to 2, right? So what exactly am I finding? What's the result of this supposed to equal?
Message.
The message. I forgot what the message was. Let me go back and look.
It's 2.
It's 2. Okay, yeah. So it's supposed to equal the message. Yeah, and we got the message. So the original message was 2. So as you can see, even decrypting it is still not super easy. It takes a lot of steps. But basically, once you take the cipher message to the power of D mod n, which that involves a lot of steps to do, then when you're done, you get the original message. But the decryption will only work though if you make sure that the encryption key is a common factor with P-1, Q-1. Like if I would have picked an encryption key of 6 or 5 or something like that, that would have worked. Then when I would have done all the steps in this message, some of those steps would have failed, and I probably would not have gotten my original message. So it's really critical that you only choose an encryption key that has no common factors with P-1 times Q-1. Yes.
So does that mean that 9 also would have worked?
Well, actually, 9 would not have worked because 9 has a common factor of 3. 11 would have worked though.
And it would have given you 2 as well.
Yeah. Now it would have given you a different encrypted result, but it still would have gotten back and it would have given you a different inverse as well. But you could have used 11 to start with. You could have used the inverse of 11 to find the decryption key. And then you could have encrypted with 11 and decrypted with the inverse of 11 and gotten the result back.
So they're many different.
Right. Yeah, that's why you can have like you can issue like more than one like key or whatever. Yeah, right. You could use many different encryption keys for the same pair of prime numbers. Yep. Okay, so any questions about anything? Yeah,
Just like a certain kind of encryption.
this is called RSA encryption. Ronald Rivest and I don't have the section of the book with me right here, but Ronald Rivest and somebody else, they were the ones who invented it. And so they just named it after their initials, I believe. So there's a guy who helped invent it. RSA encryption inventors. Ron Rivest, Adi Shamir, and Leonard Adelman, the last names. So Ron Rivest, Adi Shamir, and Leonard Adelman. R for his last name, S for his last name, and A for his last name. That's what the RSA stands for. Okay, well, that was all that we were going to learn about today, though. Do you want to do like a little workshop of encrypting something, or do you want me to, just assign you something later? So last time I taught this class, what I did is I wrote some code. Now you could write the code too, except I'm not sure how good you are at coding, to do this process in code. And then I had them use the code to like encrypt something with, and like make something encrypted and make something decrypted. Do you want to maybe work on writing a little bit of code real quick? And like, I don't think we can finish the code and get out all the bugs just in the remaining class time. But if we worked on it together, that would probably be actually a lot more educational than if I just handed you the code and I just said type f of x and then write the answer down. How does that sound? Okay, so let's work on writing some code for it. Let me do a quick check real quick. Make sure everybody's paying attention. Okay, perfect. So what do you think the code needs to do? If we write some code to do encryption with the RSA method, what do you think the code needs to do, and what do you think the code needs to be given? So let me start the sharing on this window. I think I really like computer code. How many of you like computer code? Good, perfect. Okay, so you don't have to like it, but it's just really exciting though. In fact, let's write the code actually directly within the. Well, I don't have that up anymore, but hold on a second. Let me go to like friends.edu, and then let's open up the developer tools. So let me minimize the website, maximize the console. Wow, actually, did you realize that you can actually see people's names in here when you look at that? It's interesting. And then let me clear the console by pushing the clear button. So here we have a console where we can write code in. And everything we write in this is just going to disappear at the end, though. But that's fine because I don't think I'm really ready to write like a final version of the code yet. But first of all, what are we given when we're going to encrypt something with RSA encryption? What do we have to pick before we even start? P and Q, right? So I'm going to make a comment. We have to be given P and Q, right? Is there anything else that we have to be given? Now, this is a little hard because a user might not actually know how to do this because a user of the encryption doesn't know that they have to pick a number that has to be relatively prime to P minus 1, Q minus 1, right? So you might actually have to have the computer itself generate the encryption, a random encryption key, right? So we have to be given P and Q. So do you want the code to generate it for them?
Yeah.
And so let's go do that. So then based on that, we need to generate an encryption key E that is relatively prime to P minus 1 times Q minus 1. So that's the goal, at least at first, right? Oh, I forgot. Let me share this. Let me share this on the screen. Sorry, my fault. So people can see it online. All right. Okay, it's showing. So we have to be given P and Q, then generate an encryption key that is relatively prime to that. So we need a function that can generate an encryption key, right? So I'm going to say make E. How about that? Make E. And what is the function make E going to accept as input? The P and Q, right? So it's going to take an argument of P and Q, and then it's going to, you say equals and greater than to define what the function is going to do with P and Q. Then we're going to do a long function, so we're going to do 2 curly braces around it. So right now, that's just an empty function, does nothing. But inside that function, though, hold on, how do I go back? I'm going to edit it, though. So inside of that, oops. Okay, anytime I push return, it won't let me actually edit it like an editor. Okay, so I'll have to use the arrow keys. So what can I put inside the function? How do I make something that's relatively prime to something? That's a good question. How do you put that into computer code? We could do it as an infinite loop, but then it might crash, right? So let's just assume that we're going to pick a random number. And if the random number is relatively prime, we'll return it. If it's not relatively prime, we'll keep going. How does that sound? So I'm going to do a loop that runs a maximum of 100 times. It's going to say for I equals 0, I is less than 100, I plus plus. And then it's going to have a loop body like that. Okay, now it's still not letting me type a new line for some reason, but so inside the loop body, what can I put inside the loop body? I'm going to try to create a number that's relatively prime to P. Oops, I made a mistake at the top. Does anybody notice my mistake up there? I said 1, yeah. I meant to say P minus 1 and Q minus 1. And I can't change it now because that's in the history. I can't edit my history. So how do you generate a random number between one number to another number on this language? This language has a certain way of doing it. So we're going to say variable E equals math dot floor math dot random times P minus 1 times Q minus 1. What does that statement do? That creates a random number that's between 0 to P minus 1 and Q minus 1. That's what it does, right? Oh boy, this is going to be complicated. Actually, it's going to be really hard to tell if something is relatively prime to a number. Wow. Okay, well, I don't think we can actually finish all this code in class. I forgot how tough it was. So maybe we can just skip the function, make E, and you'll have to pick your own E's. Do you think you can pick your own E's that are relatively prime to Q minus 1 and P minus 1? Because it's easy for humans to do. It's hard for a computer to do. So like, let's say, for example, if P minus 1, Q minus 1 is 115, can anybody give me a number that's relatively prime to 115? Yeah, because 7 doesn't go into 115 at all. It doesn't have any common factors with 115. Can anybody else give me a number that's relatively prime to 115? No, actually, wait, 115. Yeah, you're right. 11?
Is 3 also.
3? Yeah, 3 is because 3 goes into 120. And the difference between 120 and 5 is 5, which is not 3, so it doesn't go into it. Right. So the easiest ones to pick are ones that are prime. Now you don't really have to pick a prime number. Can anybody give me a number that's not a prime number that is relatively prime to 115? Yeah, right. Because 4 has 2 going into it, but 2 does not go into 115. Right. Okay, so anyway, but let's forget about the E part of it. We can work on that. I can work on that later, maybe for you. Let's talk about the encryption part. So let's suppose that you've already been given E before. How do I make a computer function that creates a cipher message from the original message? So how do I what should the function's name be? So how about just encrypt message? How about that? Or no, actually, because it doesn't encrypt the whole message, it encrypts a piece of it. It encrypts part of it. So to encrypt part of the message, it's going to accept what? What does it need to have input into it? The message itself, or not the whole message, but part of the message, right? And then what else? E, it needs to know the encryption key, because it's going to do the part of the message to the power of E mod n, and it also needs to know the value of n, right? So, and then once you plug those in, and by the way, you can't put a space between those, the equals and the greater than sign. Once you input the part of the message you want to encrypt and the encryption key and the value of n, by the way, we could also, instead of having the value of n given to us, we could have the value of p and q given to us, right? But that would just take 2 things instead of 1. It'd probably be faster to just take the value of n. And then what would we do? We would have a block of code. What would the first thing do that block of code would do? It would take the part of the message to the power of E, right? And then it would do mod n, right? And then return that. So it'd return that part of the message to the power of E mod n. Now, just so you know, this code will only work with small encryption powers. If your encryption power is something like 150, which it easily could be in the real world, then the computer can't do like 25 to the power of 150 in its own memory. So you'd actually have to have a loop or something that did that power slowly. And every time it did like the square of it, it would then reduce that to find the remainder. And then reduce the next step to find the remainder. Just like how we reduced our remainder, instead of having like a power of 58 or whatever, we reduced it down further and further and further. But this would work though for small exponential keys. And for small encryption keys. Then how would we write the decryption part? How do we write the decryption part? So this would accept part of the decrypted message, and it would accept the decryption key and the value of n, and then what would it do? It would return the part of the message that was encrypted already. It would raise it to the power of the decryption key, and then do mod n, right? So those were easy to write, at least without having to worry about a loop that would reduce the power if it's really big. So this code would only work for powers maybe up to about maybe 10 or 15. Because anything beyond 10 or 15 would have more than 10 or 15 digits in it. And computers can usually only accurately calculate things with maybe up to 16 digits of accuracy. So any questions so far? So do you see, even just writing the code of it is kind of a big challenge, right? At least to write the code and reduce all the steps in case it has a big power would be a really complicated challenge. So that was all that there was for today, though. But before we go on, though, does anybody have any questions about anything from the past? Like, are there any homework assignments or anything like that you're struggling with? Because I'm going to give you an assignment. It's going to be an interesting assignment. So your assignment is any assignment that you haven't gotten at least an A on before, go pick whatever your lowest assignment is, and then like redo that assignment and then upload that to the previous assignment in Moodle. So don't email it to me. Just do whatever your lowest one is again. Unless you already have A's on everything, just resubmit it, redo it, and then upload your new work to Moodle underneath the original assignment. So whatever that thing is, just redo it. And then I'll work on some code for this and try to have something for you to work with next time. Yes.
What are you gonna do for the midterm?
Well, it just depends. So I actually already have like a test written. It has some problems on it, like maybe like finding the solution to a recurrence relation and some other questions like about that, like the logical symbols and things. I'm not sure if we even necessarily really need one as long as you keep doing well on your assignments. but we possibly could maybe go ahead and have a midterm just to make sure that everybody's actually learning. Yeah.
When would the midterm be?
I would announce it like within at least a week ahead of time. So this is week 7, so week 8 is next week, right?
Yeah, but we don't have Friday.
We're not Friday. Yeah, so I don't think we're gonna have a test within like before the actual middle of the like the technical actual midterm. Yeah, just keep working on whatever I assign you the normal ones in Moodle. Yep.
Will there be like, before the midterm, will you record like, or have some sort of?
Review. Yeah, I will. Yeah, that's why. That's one reason why I would announce it ahead of time, is so that I could give you guys a review. Right. Okay. Well, keep up the good work. Thank you very much.